Okay, let me introduce you the next speaker. She's Megan Kerr from the Wellesley College. I believe I said it correctly. And she will speak about submanifolds of non-compact homogeneous spaces with special curvature properties. Okay, thank you, Megan.
Okay, thank you very much for the invitation. And the work I'm going to be talking about is all joint work with Tracy Payne at Idaho State. So very quickly, I'm going to talk about very quickly about the Ricci curvature form, and then I'm going to talk about a construction where you get a submanifold and the Ricci curvature stays the same on the submanifold as it does on the bigger manifold, and some necessary and sufficient conditions for that construction. And then I'll talk a little bit about an example that is a finite dimensional quotient of an untwisted affine Kac-Moody algebra. So if you go to what seems to me sort of exotic vocabulary, not have to, but if you go there, then it turns out that satisfies those necessary and sufficient conditions. So, all right, so I'm thinking about, so I'll be talking about solve manifolds, but to begin with, you could just think about if you have a Ricci manifold, if you have a Riemannian manifold, and then you have a submanifold, and you have the restricted metric on your submanifold. And if you have two tangent vectors tangent to the submanifold, and you look at the Ricci curvature in the ambient space, and you compare that to the Ricci curvature on the submanifold, you can ask, when do they agree? All right. And everything agrees if the submanifold is totally geodesic, but I want to allow that not to be what we have. Okay. And so in like 2011, Hiroshi Tamaru came up with a whole families of examples where he took solved manifolds corresponding to non-compact symmetric spaces. And then as a careful selection of a submanifold S prime, but you have, you have more than one way to create those S primes so that the Ricci curvature is preserved. All right. And of course, his motivation was partly that the initial solved manifold has the geometry of a symmetric space, right? It's an Einstein manifold. And so the submanifold is not a symmetric space, but it does also have that Einstein metric because it was preserved. All right, so I'm going to be looking at, oh, I see it's a little lag. Okay, that's right. I'm going to be looking at, this is probably going to be very familiar for almost everybody in the context of solved manifolds. So I'm really thinking about a solvable Lie group with a left invariant metric. But in fact, I'm going to completely think about this at the Lie algebra level. So I want to think about the corresponding Lie algebra, the tangent space to my solved manifold at the identity, and my inner product induced by the metric at the identity. I'm also going to want to be have the hypothesis that we're of Iwasawa type. So a solved manifold is of Iwasawa type, right? If you can sort of think about n, it's nil radical, and the orthogonal complement to n is A, and Iwasawa type guarantees that A is a billion, and then also that it's these two guys. So everything in A acts symmetrically relative to the inner product, and at least one element of A is positive definite on N. Okay. So as a result, due to Volter, that the Ricci curvature of the nil radical has a big impact on the Ricci curvature of the solved manifolds. And if you also let H not be the mean curvature vector for your solved manifold, so that's the vector that has the property that its inner product with Any x gives you the trace of that x for that x. And so those two things give you quite a lot of information about your Ricci curvature on the solved manifold. So the Ricci curvature on the solved manifold for two things in that abelian A, right, is the product of their adds, take the trace of that, right? And the Ricci curvature, if you have something in N, X in N, and A in A, will always be 0. And the Ricci curvature on the solved manifold for X and Y in the nil radical, right, will be the Ricci curvature on the nil radical, right, and then minus the action, the inner product of H naught, the mean curvature vector, add H of that on X, inner product with Y. And then,
Megan,
yeah.
is there a minus sign missing in part 1?
No. These guys are those should be real. I mean, is there a minus sign? I don't think so. Maybe. Well,
I mean, the Einstein constant is negative, right? So when it is Einstein, so
oh yeah. Oh, and add a, yeah. Oh yeah, there must be. You're right. We just put that in there. Sorry. Okay. Indeed. Okay. All right. So the Ricci curvature on a nilpotent algebra, right, can be thought of as with two components, and one comes, so if I think about those EIs as an orthonormal basis for the nil manifold, right, then think about summing over all your basis elements, right, and take add EI of add star of EI, right, and then subtract off what you get, 1/2 if you take add EI star of add EI. So the star represents the metric dual, right? So if I have the inner product of, say, any z with add star x on y is the same as add x on z, inner product with y. Okay, so I want to think about what happens in the symmetric setting, right? And so we can see what goes right, right? So can start with a semi-simple Lie algebra and its Cartan involution, all right? And with the Cartan involution, you can decompose G into the +1 eigenspace K and the -1 eigenspace P, and K will be your maximal compact subalgebra G, all right? And I can take B, the killing form G, and define an add K invariant inner product. B sub sigma of xy will be the negative of the killing form on x and then sigma of y. Okay, and this has a very nice property that B sub sigma, if I wanted to have add z on x and take my inner product with y, that's the same as the negative of my inner product B sigma of x with sigma of z and then y. All right, and this turns out to be quite useful for Tamaru in his construction. Table that. All right, okay, all right. So we have A, the maximal abelian subspace of P, okay, and A gives us our root system of G, right? And so if I have my root spaces, right, I have my roots. We think of the roots as the non-zero um, uh, linear actions, right? So that G alpha, the root space, is not empty, right? Or has more than 0, right? And I will also think that I have chosen some positive direction. So I have positive roots and negative roots. All right, and then we get a root space decomposition for G, all right, where G naught would be the centralizer of A and G. In my set of positive roots, I can select some fundamental roots, right? So every positive root can be written as a sum of fundamental roots. All right, and now for each root alpha, I get a root vector that has the property that the inner product of anything in A with H alpha is I apply alpha to A. Okay, and the fundamental roots, their root vectors give me a basis for A. Okay, all right. Now if I sum up the root spaces for the positive roots, I get the nil radical G. All right, and I can define the solvable Lie group by taking A plus N, and in particular, in this case where we have built this up, right? I want the inner product to be based on that B sigma, but I want a factor of 2 on the A times A part, and a factor of 1 on the N times N part. All right, okay. The corresponding simply connected solved manifold is isomorphic and isometric to the non-compact symmetric space, G mod K. All right. So that's the ambient space. All right. A basis, I can get a basis for the Cartan subalgebra A to be by taking the metric dual, right? So this is different from the root vectors. So that alpha I of H upper J is delta Ij. All right, and I'm going to use those. All right, if I take any subset of the fundamental roots, so I have some fundamental roots, I take some of them, right, and call that gamma prime. All right, and then I use their corresponding dual vectors and sum them up, and we call that vector Z the characteristic element. All right. So Hiroshi called the subalgebra that you generate the attached subalgebra. And so A prime is the span of those dual vectors, right? The H upper I's corresponding to things we selected, right? And N prime is the sum of the root spaces over all the roots that are positive on Z, our characteristic element. And now if I put those two together, A prime plus N prime, and restrict the inner product, I get what's called an attached subalgebra. All right. And this construction preserves the Ricci curvature. So it's actually pretty much follows directly from Volter and the construction being 0 on Z, which is made up of our dual basis vectors, right? So it's very easy to see, right, that the Ricci curvature on elements of A prime is going to be the same in S prime as it is in S. And the fact that A prime and N prime are orthogonal makes the next observation quite easy as well. It's the last one that's kind of interesting, that for 2 elements in the nil radical of N prime, the Ricci curvature in S prime is the same as the Ricci curvature in S. All right, and so as I have here, what you need for the third observation, right, is that the difference between the Ricci curvatures and an N prime, if you think about the Ricci, not the Ricci curvature, but the 1-1 tensor, right, then the difference is equal to the add of the difference between the mean curvature vectors. Okay, and now once you have that lemma and you combine that with Volter's results, you can see that the Ricci curvatures are going to agree on from S to S prime. Okay. All right. So just to note, other consequences of that construction is that as a submanifold of S, S prime will be minimal. All right. The trace of the second fundamental form vanishes. S prime is not, at least generically, totally geodesic. It's not typical really for that subset gamma prime of the sum of the fundamental roots and the set of the other fundamental roots. So they're not usually orthogonal sets. And as long as they're not, then you don't have a totally geodesic submanifold. Okay, so so what are the necessary and sufficient conditions for what Hiroshi Tamaru did? He had one of the things he needs is something we have called the Jacobi star condition. All right, and so in my notation here, what I want to do is sort of think about, I have an orthogonal basis on n, and then we can think of that as our orthogonal basis. So some of those, so think of these as, each of my basis vectors should be living in root spaces. That makes very good sense. So this is true of all of the EIs, and the EI primes live inside n prime, or the root spaces that are part of n prime, and EJ perps live in the root spaces that are not at n prime. Okay, and root spaces are different root spaces are mutually orthogonal. So so indeed, the perp is a reasonable notation. All right, and the Jacobi star condition that is needed is there. It looks, it's sort of it's got the same feeling of the Ricci curvature, right? That you think about, you're summing over the EJ perps in the orthogonal complement to n prime, right? And you have to add star composed with add of x should be equal to add star of x, but then minus add. You could really of the composition add EJ perp star of EJ perp, right? Could, if you wanted, imagine this sum down here. Okay, so but in particular, there's a couple of things to notice that are important. So in NES, actually, right? Oh, let's do this. In NES, right, the mean curvature vector is going to look like minus the sum over your basis, right, of add EI star on EI. Okay, and what's true in the setting where you started with a symmetric space is that add x star, that operator, is minus add of sigma of x. So in particular, the add star is an add of something, and therefore the Jacobi star condition in the box, right, is really just the Jacobi identity. It's true element by element, right? So it's true over the sum. Okay, all right. So suppose I have, I want to recreate this, all right? So I have a solvable metrically algebra, and I have make sure it's of the Iwasawa type. I have some inner product Q. I have A gives me my, it acts on N, right? I get root spaces, I have roots, right? n is nilpotent, right? So my roots are positive in some sense. I don't want them to be positive and negative, otherwise we'll get something nilpotent, right? And S looks like A plus N. Okay, all right. I can pick out my fundamental roots, right? And once I do that, right, I get their dual vectors. It's that same idea, right? Alpha I of Hj should be delta Ij. All right, and then if we pick a subset of fundamental roots, right, can we reconstruct what Tamaru did, right? So I have my orthonormal basis, right? And there's the part that's in N prime and then the other stuff, okay? I define H0 prime to be, it's right here, right? So minus sum over J, add E prime, add some J, E prime star on EJ, that's the mean curvature vector. All right, so what do we need? Okay, one thing we need is that the vector H prime defined above must lie in A. All right, the way that that will happen is here, right? So when you start with a nil manifold, your set of roots is positive, right? So if you take those roots and then you take their negatives, right? You want to know that you have an abstract root system in the inner product space A star, right? So the properties of an abstract root system, all right? And that's pretty straightforward. So it's certainly true. It's not always true, but it's true. Was true in the symmetric setting, and it can be true. That's really, so what that's really saying is that there's some universe where your set of positive roots, right, there are also negative roots, right? And then you want to know that the Weil group action on A, those reflections, right? So I think about saying, so this would be S sub alpha, right? It takes lambda to lambda minus my inner product, but on the dual space of lambda and alpha, and then alpha. All right, so, and you want to know that that takes roots to roots, positive and negative, right? And you want to know that that when a root is taken to another root, the multiplicities agree. All right, and if you have that, that's enough. So that is the, okay, so I don't want to talk too much. I don't know too much about Kac-Moody algebras. So I will try to stick with only what we need. All right, so I'm gonna start with the super easy SL3, okay? But then, and then I wanna think about, so every time you see a little circle over a Lie algebra, that denotes the sort of home base, the classical Lie algebra. What you do to get the infinite dimensional affine Kac-Moody algebra of untwisted type. I think that the loop groups, for example, are twisted. All right, and I want a real realization. So what we do is we think about it as, so I don't want to talk about the whole thing, right? Let's stick to the, so it's going to have a triangular decomposition. It has a, you could think about n sub minus n. So these are infinite dimensional. That's what the infinities do. The minus n part, you can imagine as being lower triangular. The plus infinity part we'll think of as being upper triangular. And h you could imagine as being on the diagonal, except there's no matrix here, right? So h on the Kac-Moody algebra is the old h, right? And then extended by two more, let's say basis vectors, all right? C is called the central extension, so it commutes with everything. And D is like a differential, it's a derivation, right? It takes a t derivative, but then multiplies by t. All right, but you didn't know there were any t's in here. All right, in particular, and infinity, right? So what you can think about is you take polynomials, right? Tensor with the upper triangular part of your classical simple algebra. All right, and then so all polynomials, right? And then polynomials of degree at least 1 tensor. Tensor the rest of what's in G, right? So the old H and the lower triangular elements. All right. So if SL3 has a basis, right, with the 2 diagonal guys, and then you can think of EIJ, right, is it has a 1 in the ith row and the jth column. All right. That's a nice orthonormal basis for on this guy, right? SL3 has these nice positive roots, alpha 1, alpha 2, and there's some alpha 1 plus alpha 2. And they correspond to, this is this is generating the root space, right, for alpha 1, E12, E23 is generating the root space for alpha 2, and E13 is generating the root space for alpha 1 plus alpha 2. But then but our nilpotent guy is also has basis of just powers of t, right? Tensor anything in SL3. So, all right, and as a basis, you can think about taking basis elements of SL3, right? Tensored with t to a positive power. Okay, all right. Oh, let's see. All right, now n was infinite dimensional, and what we do is we mod out by the ideal of, this is a graded Lie algebra, so we're gonna mod out by the stuff of grade bigger than m, right? So as after you throw away things that have t to the k plus l, where k plus l is bigger than m, we'll just say, if that happens, then these two guys commute, right? And otherwise, it's my Lie algebra. So this is a truncated version that comes from a quotient of the nil radical of a Kac-Moody algebra. Okay, all right. So I want to point out that the roots, so the roots look like the original roots, right? And then plus some multiple of delta, all right? And then the original roots, and then just the multiple of delta, all right? Delta takes d to 1, it sends c to 0, and sends all of the original things in h to 0 as well. All right. Okay. All right. Although I said notice, I think you have to just take my word for it that the delta union, it's negative, forms an abstract root system. Okay. I give it some of the root spaces, right? G alpha 1, G alpha 2, G alpha 1, right? And here are the G and deltas. And then, but the roots also include, right, like, 3 delta minus alpha 1, right? Any of the old roots, right, for SL3, right, and then add it on to any multiple of delta, right? N goes from 1 to m. Okay. And then, so this construction, right, does satisfy the proposition I said before, right? We have a nice root system, and where's the other piece? we have to, the while group action on Kac-Moody algebras preserves dimension and takes roots to roots. It's all the nice properties that we have for nice simple semi-simple algebras. All right. And that's enough to give us H naught prime to be where it's supposed to be, right? And to let us make a subalgebra, right, with whose Ricci curvature is preserved. Okay. All right, and this is kind of interesting because you can think about what happens if you're in this setting, but the fundamental root you decide to drop is the one that has delta, right? So, for example, right, you could, so this is the right, or you could have one of your new root, right, but also one of your old roots, etc. All right, and so this is a brave new world, or a brave new world for us. We're exploring the geometry of these guys. Thank you very much.
Thank you, Megan. Thanks for your nice talk. And are there any comments or questions for Megan? I would like to ask, how did the Kac-Moody algebras appear this scene? How did you come up with that?
Oh gosh, I think, I mean, somebody got inspired. That somebody was Tracy. So, you're saying like why look there at all, right? And I think he knew enough about them to know that they do have those nice sort of root space file group properties.
Okay, good.
Yeah. They have that hidden, in my mind, it's sort of think about like if N is upper triangular, what makes this work is that somewhere is the lower triangular stuff.
Okay. And this, you have given us just an example for SL3. Maybe you can do it.
Yeah, you could do this for, I mean, okay, SLN has a nice property that all of the roots are the same length, right? Or like Dinga diagram, or those are the same numbers. I mean, the Kac-Moody properties seem to be true for, you could base it off of any of your favorite simple algebras. But it might be a little stickier. But certainly SL3, it could be SLN. Yeah.
Okay. A whole new world, as you said.
Right.
Is there any other question for Megan? If it's not the case, well, let's thank Megan again. And we continue in